Okay, so let's start.
Yes, excellent.
Yes, okay, can you see it full screen now?
Yes.
Okay, great.
Perfect.
So, yeah, thanks for the invitation. I'm very happy I made it. I was teaching just a few minutes before I got into this meeting room. And I'm going to talk about tropical and southwestern Atlantic Ocean biogeochemistry modeling. And more than show results, I'm going to discuss with you the needs and the gaps. I'm going to tell you a story that goes back to the time I was working in Germany, in Jena. So, and I had the help from Raquel Oliveira. Raquel was an inclined student in 2021, and she's now, she also has a developing project from the incline school, and I'm very happy with the results. This is the very end. So okay, so now Melly has now introduced me. So yeah, I'm now an associate professor at UERJ. That's where I got my bachelor degree. I co-lead the Brazilian Research Network for Ocean Acidification. I'm also in the Climate Research Network in Brazil, and I was part of the IPCC, the last IPCC report, the AR6. And here are some few pictures of where I've been and things I like doing. I like going to the beach a lot. So, and I also enjoy being on board vessels. And I divided the talk today into having this look into Brazil and the South and tropical Atlantic Ocean, modeling first, the modeling efforts, then I'm going to show you a few of the observing efforts, and then let's see what we need and how to get there. So modeling efforts. So I'm bringing here, it's not an exhaustive list, so I'm just showing you a few examples. This is a position paper. I was a co-author that came out in 2021 on the coastal ocean observing and modeling systems in Brazil. So what we have in place, and then a little bit about the future perspectives. And then I picked two examples of things that are already in place in Brazil for oceanographic modeling. So one is the REMO network. So it's basically operational oceanography for, they do both forecast and hindcast, but they are very, very focused on physical parameters. So they use data simulation a lot, and they use the South Atlantic along the Brazilian margin and also offshore. So they use 1/24 of a degree. So it's and everything is based on HICOM model. So this is one example. And then they could run biogeochemistry, but I guess, if I'm not wrong, at the moment they're most focused on circulation and other physical outputs. And then another example, much more coastal, is from the Brazilian Sea Observatory. It's in between Paraná and Santa Catarina. So they do a lot of coastal monitoring and also operational modeling. And they integrate different types of data into this observatory. And one of the ideas is also to produce like an on-demand tool to know where the hypothetical oil spills could be. And they use the community model, the MEMS, and they use a 12th of a degree forecast model for some of the purposes. And I put this here, this orange arrow here. They don't have biogeochemistry, and for this very coastal specific area, there are not enough data for biogeochemistry, so to run and especially to validate the model. So Paula was talking about Cananéia, just to give you an idea. Cananéia is here, and this is more on the further south, where they focus. And then talking about ecosystem modeling, biogeochemistry modeling, this is an issue. This is a gap for, I'm sorry, this slide is in Portuguese. This is from the PROA network. And we had we asked people around for the, how were they were tackling ocean acidification, and which type of studies they were doing. And very, very few answer about ocean and biogeochemistry modeling, focused on acidification. And if you see, the green color is not here in the pizza graphic at all. So this is a gap we have identified, and we had already identified it 10 years ago when we started the network. And just to say, so there's absolutely no biogeochemistry in the South Atlantic. And I said, that's not true. And there's, again, I'm not being exhaustive. I'm showing it's a personal experience on biogeochemistry modeling. And this is why I'm going to go back in time a lot now. Okay, so a bit less than 10 years now. And this is the outputs of a paper with my co-authors, Eric Baltenhaus, Corinne Lequiré, Xavier Giraud, and Wolfgang Ludwig from Perpignan. So the idea was to understand, so what happens to riverine carbon and nutrient inputs in the ocean? So we used general ocean model coupled with biogeochemistry. So, and the first idea is, why do we have to represent biogeochemistry in global ocean models? Well, we need to understand biogeochemistry not only for this ocean atmospheric CO2 and other greenhouse gases exchange, but also to have this idea as a whole, how coastal oceans, they respond to this human influence and also to climate change. We also know that land use changes completely the nutrient transport by rivers, because we have use of fertilizers in agriculture, inputs of organic carbon from sewage, and etc. And this may have also possible impacts on regional fisheries, not only from what comes from the continent, but also the chemical behavior of the ocean itself. So we still do have uncertainty in CO2 fluxes, atmospheric CO2 fluxes in coastal areas. And coastal areas are so important. They are home for 80% of the new production, also a very large amounts of the nitrous oxide and methane emissions to the atmosphere happen around the coastal areas. And so this is the main results that came out using this biogeochemical model, and we used an ecological model called PISCAS-T at the time. So overall, they do have river inputs and carbon. They have a modest impact on global ocean biogeochemistry regarding sea air, CO2 fluxes, primary production, export production. So the primary production changes are from 16 to up to 5%, depending on the scenarios we were discussing. And sometimes the increase in primary production is also counterbalanced because rivers also bring organic carbon. This is outgassed close by in the continental margin areas, according to the model. This is what the model is suggesting. And they are also suggesting that there's a big regional variability of this nutrient and carbon impact on biogeochemistry, and it's really depending on local nutrient limitation. So sometimes river inputs alleviate nutrient limitation, and then we have an enhancement on primary production. And what we saw using this model is that the tropical Atlantic is especially sensible for these riverine inputs. There was really increase in diatoms, which also forced the export production in the model, increase in chlorophyll. So these two maps are in chlorophyll. And so we decided to run on top of this sensitivity models focusing on the tropical Atlantic Ocean that receives 1/5 of the whole world's river freshwater input. We have large rivers there. And so this came out in 2013, focusing on the tropical Atlantic. And then from the main results is that there are different impacts on coastal primary production and export production, comparing the South American rivers with the African rivers. But at some point, the African rivers, they have a larger impact on the whole tropical Atlantic, because there's a combination on the Eastern Atlantic, so along the African continent, that oceanographic features of upwelling areas and of the large rivers outflow, and also shallow mixed layers and different carbon and nutrient ratios, they may somehow fuel the primary production. So despite having in absolute numbers of input of carbon and nutrients, the impact is higher, considering this area between 20 degrees north and 20 degrees south. And now, and I just saw there's just came out 2023, like another, using a more advanced, like a more modern model in using these future scenarios from the considering climate change. In these other two papers I showed you, we didn't look into climate change. So river inputs, they have to be considered into these models, because there is a difference, and they may alleviate the primary production within this warmer and more stratified open ocean areas for the future scenarios. So now we saw what's going on with the modeling, and now let's check observation. So this is a map for the Global Ocean Acidification Observing Network, and this circle is, again, the tropical Atlantic. So there are things going on observing carbon parameters. We also have lots of data from the Global Ocean Data Analysis Project, GLODAP, and this is where GLODAP has recorded and organized data. So this is also open to everyone. And again, the tropical Atlantic, it looks like there's a lot, but then when you take a closer look of the Western Atlantic, there isn't that many observations. So this is something that sometimes is not very helpful for validating model results. And from an observation point of view, so we do have a manuscript that has been submitted to Journal of Marine Systems from one of our students, Carlos Musetti. So he used temperature and salinity and an empirical model. So it's a very simple model into this location here in the Atlantic. So that's where I lost my, here. So where this, the red circle is, and fugacity of along the surface of the Atlantic Ocean in time is, it's increasing. So we use this empirical model, and it could reproduce the trends from observations from SOCAT, for instance. And we also estimated the decrease in pH, which also corresponds to other models and other estimates of acidification. So, this is being submitted, it's, being reviewed at the moment. And because we saw that, well, there's not many data on biogeochemistry, riverine inputs, and so on for coastal. So what do we need if you want to better assess, for instance, the CO2 fluxes along the margin? So here I'm showing you the two studies that are already in press. One is in Ocean and Coastal Research, which is the new name for the Brazilian Journal of Brazilian Oceanography paper, journal, sorry. And so this is a paper from AFE, and she divided Brazil using the ecoregion system. So she's already taking a look. So what's biological influence? What is pure physical chemical processes controlling the sea air CO2 fluxes? And here we estimated the whole fluxes, but again, we are also interested in what's happening with time trends and also the role of biology, so the plankton groups. I'm always now getting to the end of this talk. And this is a review study from Raquel Oliveira, and she's here and with us today. So she dedicated to regional observation and modeling efforts along the Brazilian margin. So there are many studies, much more on the like open ocean areas, much more than really local along the continental margin. So, and it's the Brazilian margin is like a puzzle of being source, changing from source to sink, depending on the different oceanographic features, also regional features. And to get there, so the strategy we are using now, and this is the task of Raquel and in her PhD, is to combine biogeochemical observations from databases and also dedicated projects for this area. And the names of the projects are now Seascope and Flux C2. This is ongoing here at UERJ. And the idea is to link data and the modeling community and for us to have a tool for constraining marine carbon and basically CO2 for climate studies. And so this is one of the projects. So it's funded by the German BMBF, so led by the colleagues from Guiomar, and UERJ is part of it. And we are running now, since November, an autonomous CO2 and methane system, and we also cooperating with the FSU University, so in Jena. So Professor Karel she's running the MIT GCM model, focusing on biogeochemistry of the tropical Atlantic Ocean. So the area where you're doing the measurements. And Raquel's own project is on the South Atlantic biogeochemistry responses regarding the AR5, so the last IPCC report, and she's using EcoGenie, which is a Earth system model, and the goal is to check under these future climate scenarios, how will the biogeochemistry in the region behave, and because and use the plankton groups and divided by the different sizes, but also the ecosystem functions, and focusing on the tropical and subtropical Atlantic Ocean by 2100. So this is work in progress, and this is more or less how the EcoGenie system works. And so we're really trying to get more biological processes for the carbon. And there's going to be 3 scenarios. So one is no forcing, so without the climate change. And one scenario is optimistic, using the RCP 4.5, and the other is a pessimistic scenario from RCP 8.5. So this is like the very, very first result. So Raquel is running, is still analyzing the results for the Atlantic Ocean. And there's going to be more to come and soon, I guess. And so, as I told you, this is still work in progress. And with that, I finished the talk, and I really want to thank all the colleagues at the Chemical Oceanographic Lab at UERJ, and also the Seascope team in Guiomar and Jena. And also, again, thanks the Symposium team for the invitation. So I'll leave you my email address here, and then my social media at Let Cotrim if you want to contact me. Okay, so that's it. I'll stop sharing, and then we can go back to any slides when you need. And thanks again for your attention.